This is your final vodcasted lecture for the week, and if you're watching it from the regularly scheduled lecture hall, then this is Friday, March the 6th, and hopefully at this point we're beginning to be celebrating a double national championship in Bend, Oregon. Fingers crossed, right? You're probably thinking, why are there so few announcements today on the things to remember? And that's for one of two possible reasons. One is that maybe there's that few things that we need to think about. Two is that this far in advance, maybe I'm forgetting something that I'm supposed to be telling you. And it could be the latter, and therefore I will plan to email you and make announcements on WIO courses when it gets closer to the time, so that just in case I've forgotten something, expect some sort of communication from me via that method. But in any case, if you have not yet revised your hypotheses for your poster groups, please do so and send those back to me. Of course, you may be waiting on me to still give feedback to you, and so I imagine depending upon when I received your hypothesis, I'll be turning that around and returning feedback to you. And once you get that, try to turn it back around so that it doesn't get stale. You know how it goes when it gets stale. That's just no fun. No fun with bread, no fun with hypotheses. So homework 5 is due on March the 10th. So that's this coming Tuesday. Don't forget to get that done. Of course, we'll have everything as normal on Monday for office hours and whatnot. So feel free to come and get help on that if you need any help. The rubric skill assessments are coming due rather rapidly, so think about getting those done and maybe coming to Open Lab today and getting a few of those taken care of and knocked out. Wonderful. Let's jump right in because we need to talk about the first fate of pyruvate. Remember, we talked about the favorite fate of pyruvate last time, which is fermentation. However, we never got to talking about the first fate, and that is this idea that pyruvate, despite the fact that it is already relatively oxidized, especially as compared to glucose, it still has energy left in those bonds. That is to say, it can still get further oxidized. So that is what fate number 1 is further oxidation. So we're looking to see that occurring within the mitochondrial matrix of eukaryotic cells within the cytosol of prokaryotic cells. Now, I've sort of partially written this out. Do take note that both pyruvates would come into the mitochondrial matrix, and both of them would be oxidized. Sometimes we just show this for one pyruvate because, quite simply, it's a little bit easier to think about it that way because only one pyruvate can enter in the top of the Tca cycle, and we do know that that will be what will occur to that pyruvate next, is to go to the top of the Tca. So we can make mention of that the next step here is entry into the Tca cycle, and all of the steps of the Tca are what we're going to be looking at today, so you can get jazzed for that. And I'm literally scratching out a skeleton outline of the fact that we're going to have 1, 2, 3, 4, 5, 6, and oh boy, that was a rough arrow. You're laughing. 7 and 8 steps of that Tca. But in any case, bad arrows and everything, this is the Tca cycle that we'll be looking at today. So that says Tca. So we know that as pyruvate gets further oxidized in what we sometimes call the transition step, so this step here is the transition step, we know that an NADH is generated in that process. However, we also know there are a couple of other nuances to this reaction. We know that a thoroughly worn out, fully used up, totally, entirely oxidized carbon dioxide gets lost also in this step. So we see the loss of a CO2. We also recognize that the coenzyme A that carries the acetyl group around, the taxicab for the acetyl group, is of course a co-substrate, right, because it can move around. We know that it has to get added in during this reaction. So coenzyme A joins the party, so to speak, in the transition step, and then it can effectively carry that acetyl group. So there's a little more to that we didn't originally have written onto the reaction. And I really want to take our attention now to this reaction called the transition step. And I want to look at the process by which pyruvate gets oxidized to acetyl-CoA. So without further ado, we'll take our attention there. So this reaction is a relatively exciting one. As we saw earlier, it's the conversion of pyruvate to acetyl-CoA. We can make note that both of the pyruvates undergo that conversion. So in essence, 2 pyruvates from each glucose would yield 2 acetyl-CoAs. We also know that then that would mean that 2 coenzyme A's would have to be consumed in order to carry around the acetyl groups, so getting 2 taxicabs added on. 2 thoroughly worn out CO2s, and of course the generation of that reducing power. So NADH is a product of the transition step. We also talked about the fact that in a eukaryotic cell, this happens in the mitochondrial matrix. Of course, in a prokaryotic cell that doesn't have a mitochondrion, it's going to happen in the cytosol. So 2 different compartments. This is the first time that we've seen that, because remember that glycolysis, the Ebden-Meyerhof pathway, the Ettner-Dudorov pathway, the penose phosphate pathway, all of those rad glucose degrading pathways all took place in the cytosol of the cell, no matter whether you were talking about a eukaryotic cell or a prokaryotic cell, whether we were looking at a bacterium or an archaean or a ciliophoria, right? Some sort of protist, it always occurs in the cytosol of any of those cells. But this is where we start to see compartmentation. We start to see that the transition step, further oxidation, is going to take place in the mitochondrial matrix of that eukaryotic cell. So let's take a look at the Tca cycle, and I bet some of you know it by another name. Maybe you call it the Krebs cycle or the citric acid cycle. Either way, it's just calling it by another name. It's all the same darn thing, but different terms for it. In fact, we'll see momentarily why the citric acid is a name that is often given to the cycle, because in fact citrate or citric acid is the intermediate of the first step of the cycle. So let's talk about some of the facts. It does occur in the cytoplasm of prokaryotic cells and in the mitochondrial matrix of the eukaryotic cells. It's not as ubiquitous as glycolysis or Ebden-Meyerhof pathway was. In fact, we're going to meet a little bit later in the semester, like you can be waiting with breathless anticipation, some really crazy archaea that do not have a functional Tca cycle, or that have some of the enzymes in the Tca or alternative enzymes to the Tca, so it's not a traditional Krebs cycle. So we're going to see some diversity there. However, it is functional in a lot of bacteria, many protists, and most fungi. It also is a sweet amphibolic pathway, so it has a dual nature as well. That is to say that we know that the primary purpose of this pathway is breakdown. We know the primary purpose is generation of reducing power, but it also makes a lot of precursor metabolites. In fact, for example, one of the intermediates in the Tca cycle is used to make glutamate and aspartate. So these very familiar amino acids that, we still have tables up above the toilet of, you might stare at those every day and think, oh, interesting, I wonder how glutamate and aspartate get made. Well, they're made from intermediates of the Tca cycle. So we can say that overarchingly, the goal of the Tca is to break down, to completely oxidize, totally strip all of the potential electron energy that are stored on the 2-carbon moiety of the acetyl group. That's the primary goal. So to those ends, we know that in fact, when this 2-carbon group gets oxidized, it in fact will lead to the production of 2 thoroughly worn out, fully used up CO2s. So to answer this question, how many CO2s? Obviously, there are 2, because this is a 2-carbon acetyl group. So for every acetyl group that enters into the top of the Tca cycle, we know that there will be 2 CO2 molecules that are lost. So I'm going to jot it down, because I know some of you you're zoning out. You're like, Rachel's not really here. She's not going to know if I'm zoning out. Yes, I totes am. So definitely wake up. So 2 CO2s are going to be given off there. Okay, Taylor, wake up. 2 CO2s, whoa, we're all set. I used to have a little baby squirt gun that I used to carry around in the lecture hall just in case people fell asleep. I need to revitalize that baby squirt gun. I'm totally going to do that. So 2 CO2s are lost in the complete oxidation of this 2-carbon acetyl group. Wow, we're ready for the journey through the TCA cycle. So let's take a moment to gear up and dive in so that we can see what occurs in one turn of the TCA. Here we have it, the TCA cycle in its absolute full glory. We are going to deconstruct every single step, beginning with the first step, which is perhaps arguably the most interesting step, because in a pathway that is entirely focused on oxidation, on breakdown, on degradation, step one is an anomaly. That is, it is a condensation, a synthesis reaction, a reaction in which a bigger molecule is built from two smaller molecules. So it is sort of the odd man out as far as steps in the TCA cycle go. It is the only step that is a building step in this pathway. So we could even say, in fact, that it is an anabolic step within a catabolic pathway. And the product of this step is going to be a much larger molecule than are the reactants. So to begin with, we know that we had our acetyl-CoA molecule arriving from the transition step. We know that this 2-carbon acetyl group is getting carried by the coenzyme A taxicab. The coenzyme A taxicab actually turns out to be more than just a taxicab. This is a taxicab with a big perk, because the bond, the covalent linkage between the coenzyme A and the acetyl group is a wicked high energy thioester bond, right? I know Jonathan and Jake, you guys are picturing how sexy is a thioester bond, a C double bond O bond S, and we recognize that as being enough energy in that bond to actually power the synthesis of this larger molecule. So when that bond breaks, this actually is what provides the needed energy to synthesize the 6-carbon citrate from the 4-carbon oxaloacetate and the 2-carbon acetyl group. So the last intermediate of the TCA cycle is the 4-carbon oxaloacetate. It then gets the acetyl group added onto it to form citrate. And in fact, we often call this first reaction of the TCA an incorporation step, because the 2-carbon acetyl group is getting incorporated onto the intermediate oxaloacetate, and we're forming now a molecule that carries that 2-carbon acetyl group. And note, this is also the molecule for which the TCA cycle is named, the citric acid cycle, citrate or citric acid. Citric acid is, as you can see, a 6-carbon molecule. You may also, if you're just real jazzed about chemistry, be recognizing that this is a tertiary alcohol. Now, a tertiary alcohol is pretty sweet, but in fact, this molecule is not readily oxidized. Therefore, the second step of the TCA cycle is a lot like the second step of glycolysis in that it is just a rearrangement. Now, seemingly boring, this rearrangement is actually epically important, because tertiary alcohols don't get readily oxidized, whereas after rearrangement to form a secondary alcohol called isocitrate, this molecule is readily oxidizable. And so now we're ready to do it. The first step for which the TCA cycle, I joke its middle name, right, is reducing power. Well, this is the first step that is truly representative of that label, because isocitrate gets oxidized in step number 3. And as we know, with any good oxidation, where electrons are ripped off, those electrons don't run around naked. They get carried like any decent electron would by an NAD plus molecule. So the NAD plus molecule will take on those electrons, becoming NADH. Isocitrate gets oxidized, NAD plus gets reduced, and we get the production of the intermediate alpha ketoglutarate and the high energy reducing power NADH. It, of course, just is going to get the heck out of Dodge. Remember that it is a co-substrate, so it can dissociate from the enzyme active site. It's going to run its electrons to the ETC, drop them off, and then, of course, the NAD plus can come back and pick up more electrons. So the isocitrate is getting oxidized, but not only that, I want you to look at something here, and I doubt you're getting bored yet, but maybe if you were getting bored, you were counting carbons, 1, 2, 3, 4, 5, 6. Ooh, yes, of course, isocitrate, just like citrate, is a 6-carbon intermediate. But recognize this, alpha ketoglutarate, 1, 2, 3, 4, 5. A carbon is lost. Actually, look at this, a CO2, a carbon dioxide, a thoroughly worn out, totally used up, fully oxidized CO2 is given off in this step. So catch this. This step is not only an oxidation, but it is also a decarboxylation. So we're seeing, this is like, honestly, seriously, could there be anything sexier than an oxidative decarboxylation? I mean, the next time you're just at a dinner party and you're at a loss for words, just say it. Isocitrate gets oxidatively decarboxylated. And honestly, who could not enjoy that? So we see the production of both reducing power and a CO2 in an oxidative decarboxylation. Now here's where you get to find out that enzyme naming continues to be epically easy. And in fact, just as we knew that every time we saw a phosphoryl group transfer take place, that was a kinase, now we can come to understand that every time we see the oxidation of an intermediate, the name of the enzyme is going to be either dehydrogenase or oxidoreductase, and that'll be the second name. And the first name is going to be the name of the molecule that gets oxidized. So isocitrate dehydrogenase, that's going to be the name of this enzyme. Cool, really cool, because we get to do it again. That is another oxidative decarboxylation, right? What could be better than one? How about two? Alpha ketoglutarate is going to get oxidatively decarboxylated to form succinyl-CoA. In a reaction that I have a feeling you might think, am I having deja vu? Because in this reaction, we get the production of NADH in the oxidation of alpha ketoglutarate. We get the production of a thoroughly worn out, totally used up CO2. And we also get the addition of coenzyme A. Now tell me, what step does that remind you of? A recent one that we talked about. And in fact, that brings me to a point. I have an epic extra credit opportunity for you. If you come to me on Tuesday in lab with a rough draft of your poster and you show me that rough draft and you tell me how you've learned how to name enzymes such that you can tell me the name of the enzyme that catalyzes the transition step, and you can also tell me what that step resembles, then I'll give you extra credit. Obviously, much of that extra credit is because I would love to see a draft of your poster because I really think they're cool and I really want to see what creative things you're coming up with. But also because I'm curious to see if you're understanding this whole enzyme naming thing, because look here, here's another oxidation. Alpha ketoglutarate is oxidized to produce NADH, so I bet the name of that enzyme, alpha ketoglutarate dehydrogenase. You got it, absolutely. So we get the synthesis of the intermediate succinyl-CoA, and you might think, I bet that's another wicked high energy thioester bond. It is, indeed. In fact, I want you to go back right now into your phosphoryl group transfer potential table, and I want you to look up the free energy, that is the possible energy pent up in these bonds of succinyl-CoA, and tell me whether there's enough to make ATP. Do it. Not just because I'm there doesn't mean you can slack off, right? So, okay, seriously, pick up your table, look it up, check it out, and tell me what is the capacity of that succinyl-CoA. And hopefully you're finding out that it has enough energy to produce ATP. And in fact, step number 5 of the Tca cycle is the only step in which ATP is generated. Wait a minute. Didn't I just say ATP was generated? Hopefully some of you are starting to come to a realization. I can see like a light bulb go on in Dylan's head and he's like, wait a minute. GTP is exactly the same energetically as ATP. That is, I bet GTP could quickly transfer a phosphoryl group onto ADP to make ATP, and then basically this is energetically equivalent to ATP. Dylan, if you were thinking that, you're so rad because you were perfectly right. These are universal energy currencies that certainly can be easily transferred one form to another. So we see in step number 5, the first and only step in which ATP is synthesized. We also see the production of actually a real sexy molecule, because look at this. This is the Denzel Washington molecule of the Tca cycle, because notice that this molecule is symmetrical. And in fact, it's the first molecule that we've seen in the Tca cycle that's completely symmetrical. It's actually the point at which we lose track of the carbons because they're perfectly symmetrical. So succinate is formed, and it's so cool because succinate, this epically good-looking molecule, is acted on by my favorite enzyme of all time. Now, this enzyme oxidizes succinate, only it doesn't form NADH in that oxidation. Instead, it forms FADH2. Now, we all remember that FADH2 is a prosthetic group rather than a co-substrate, so it can't dissociate from the enzyme active site. So the next mobile carrier, the next mover and shaker of electrons is QH2. QH2 can carry those electrons on in the into the electron transport chain. So it's the next one that can get around. Now, in a moment, I'm going to tell you more about this epic enzyme, Succinate Dehydrogenase, right? You could have named that right off, but I like to also call it Wonder Woman enzyme. More on that later. Fumarate can get hydrated now to form the last intermediate, malate, and malate gets oxidized yet one more time. So yes, again, yet again. Yeah, I feel like Star Wars, right, Totes? There is another NADH, right? We get the production of a third NADH molecule. So now, as promised, I want to tell you a little bit about succinate dehydrogenase. Succinate dehydrogenase, Wonder Woman enzyme, is what I call it that because succinate dehydrogenase not only catalyzes step 6 of the Tca cycle, where it does a good job of oxidizing succinate to fumarate, however, it also, get this, is in fact a membrane-spanning or integral membrane protein that is also complex 2 of the electron transport chain. Yeah, seriously. So just like Wonder Woman, Diana Prince by day, Wonder Woman by night, like you guys are way too young for this, but I'm hoping that some of you have some sort of like infatuation with old bad movies or bad shows. So in any case, succinate dehydrogenase is capable of not only being the catalytic enzyme that allows step 6 of the TCA to take place, but it also is complex to the integral membrane, spanning complex of the ETC that acts as the, you know how we were making that analogy, and I'm thinking Sammy, she's loving this right now, that made that analogy to the ETC being like a highway where there are different entry points. You could think of succinate dehydrogenase as being one of the entry points, and in fact it is the entry point for FADH2 electrons. So it's an amazing multitasker in that way. Before we leave this slide behind and I promise more later on succinate dehydrogenase, but I want to make sure we answer this question. How many times does the Tca cycle turn for each glucose molecule? And I think this question deserves an awkward silence moment. So I don't know who's going to feel the most awkward in this awkward silence. You know, probably me. But in any case, I'm being awkward for a minute. Actually, that wasn't awkward at all. That actually felt really nice. I did like a little yoga breathing. That was great. So hopefully you now are thinking, I know that for every one glucose molecule, 2 pyruvates are made. And then, of course, those 2 pyruvates each are turned into an acetyl-CoA in the transition step. So the Tca cycle is going to turn twice for each glucose that is fully oxidized. So that's a really important thing to bear in mind. Of course, it's really important when we're considering yield. So I want to think about what would the yield of this pathway be for one turn, right? How much reducing power, how much ATP would be made if we were thinking about one turn of the cycle. So let's just give that a look. In step 3, we get an NADH. In step 4, another NADH. Okay, so I'm keeping tally on the NADHs. 1, step 4, 2, and step 8, 3, right? So a total of 3 NADHs are made per turn of the TCA cycle. Of course, we know the cycle turns twice if we're talking about a glucose, so we would need to double that, and we could say, complex math, 6 are going to be formed from one glucose being fully oxidized, right? So if we see the math coming out for a glucose molecule being completely and utterly fully oxidized, we would have to assume 2 acetyl groups, 2 turns of the TCA. But I don't want you to blindly memorize just how much energy is net or how much reducing power is net from a glucose molecule. I want you to think about it. I want you to be able to come back to your posters, and I want you to be able to say, if 1 acetyl group is oxidized, there are 3 NADHs per turn. If 2 acetyl groups are oxidized, there would be 3 NADHs per turn. Hey, what about if a fatty acid is oxidized and has 18 acetyl groups? Right? How many times then does the TCA cycle turn? How many NADHs then are made? Ooh, that's something you could also tell me when you come to me with that extra credit. 18 carbon long fatty acid, what would happen then? Okay, so now let's go ahead and write down the net yield of ATP, NADH, and FADH2 for both 1 acetyl and 1 glucose. Oh, and of course you guys knew that that enzyme name was malate dehydrogenase, right? You did know that, didn't you? Oh boy, I'm going to have to go back. Rapid review of the TCA cycle, right on. So we get this 2-carbon acetyl group gets incorporated to form citrate. Citrate-citric acid cycle, the molecule for which this pathway is named. Acetonitrate works on that 6-carbon molecule rearrangement, epic rearrangement, because now we get a secondary alcohol that is very easily oxidized to form an NADH. It's an oxidative decarboxylation because, of course, the CO2 is lost. We know that enzymes are named isocitrate plus dehydrogenase, and we see that again in step number 4. We see an alpha-ketoglutarate getting oxidized succinate-CoA. We recognize the generation of high-energy reducing power takes the electron transporting. This is also an oxidative decarboxylation, loss of CO2. Alpha-ketoglutarate is the name of the enzyme because we know that it is always the name of the substrate plus dehydrogenase. Succinate-CoA, wicked high energy. Remember, look at the phosphoryl group transfer potentials. We know that that molecule can be tapped into now to generate ATP. It generates ATP or maybe GTP. GTP can get phosphorylated in ATP to make it ATP. It's energy equivalency. Now succinate, Wonder Woman enzyme. Now we recognize Wonder Woman enzyme gets on board, takes succinate, oxidizes it, makes FADH2, but FADH2 can't leave the active site of the enzyme, so it has to transfer its electrons onto Q. Q becomes QH2. QH2 can now run along. Fumarate now gets hydrated, and we get malate. Malate, the last intermediate of the TCA cycle. Malate can be oxidized. We get the generation of NADH, and it's the last NADH. We know there are 3 per every turn of the TCA cycle, and that's where we were. So now let's look at the overall yield. 1 ATP per turn in that step number 5, 2 ATP per glucose. We know that if 1 glucose is made, the TCA cycle turns twice, so we would get 2 ATP. We also can likewise recognize there are 3 NADHs that are formed for every 1 turn, meaning that if a glucose is oxidized fully, then there would be 6 NADHs, just multiplying by 2, right? 1 FADH2 for every 1 turn. Remember, that only happens at step 6 at the epic Wonder Woman enzyme step. 2 FADH2s would be net for every 1 glucose that was fully oxidized. And it's also worthy of our attention to remember that the TCA cycle also generates precursor metabolites. That is, there are many molecules within the TCA cycle that can get utilized as Legos in the process of building other larger molecules. Good example of that is alpha-ketoglutarate. Remember, alpha-ketoglutarate formed in one of the oxidative decarboxylations. That alpha-ketoglutarate can serve as the precursor metabolite, the Lego upon which building of glutamate and aspartate can take place. Succinyl-CoA can be used to build porphyrins. Oxaloacetate can be used to build other amino acids. So a lot of these are biosynthetic precursor metabolites, thus giving the TCA that epic name of amphibolic. So let's do just a little bit of math. If 1.2 times 10 to the 18th molecules of glucose are catabolized, how many ATP molecules are net via substrate level phosphorylation during glycolysis and the TCA? Okay, so we've got a few things to consider here. So recognize that we're looking at both pathways, and of course we know that substrate level phosphorylation will encompass all of those ATPs that are made directly in the pathway. It just doesn't account for any of that reducing power, any of the NADH that'll eventually make ATPs via oxphos. So for now, we're just focused in on substrate level phosphorylation. So we can think about what happens in glycolysis. So remember, in glycolysis, there were 2 ATPs that were net. So 2 ATPs, glycolysis. And then remember that in the TCA cycle, there was 1 ATP that was made per turn, but notice here that we're looking per glucose, so it's going to have to be doubled because the cycle turns twice. So 2 ATP from TCA. So basically what we're looking at here is 4 ATP via substrate level phosphorylation times how many glucose molecules? 1.2, so this is 4 ATP per glucose times 1.2 times 10 to the 18th molecules of glucose. And we're all set up to cancel some sweet units. And we've got it, right? I mean, basically we're looking at 4.8 times 10 to the 18th ATPs. See, you thought that was going to be hard. We're totally solid, however. So now we can think about the potential that's out there to make more ATPs via oxphos, and we're finally going to take our journey through the electron transport chain and see all of the full glory of that chain.